When we consider the problem of finding areas under curves, one of the features of a function that often comes in handy, surprisingly often, are properties like the evenness and oddness of a function. Now these are even and odd in the sense of 1, 2, 3, 4, not odd as in strange. So if we have an even function, for those who have not seen this before, an even function satisfies this relationship here, that if I plug in an x value or I plug in the same value but negative, I get the same function out. Another way to write this in words is symmetric across x equals 0. Now some examples would be, let's draw a few here. Y equals x squared. There we go, a nice parabola like this. That would be a symmetric function in the sense that it's even. If I go to positive x equals 1 or negative x equals 1, I get the same y value. Another example would be cosine of x. There we go. Cos of x is an even function. Cos of x is an even function. Other functions that we might see, nice thing about, or one of the roots for the even odd is actually the powers that we get with y equals x to some power. If we had y equals x to the fourth, it would also be an even function. It would be a little steeper, a little lower at the beginning, but that would be another even function in our catalog. And combinations of even functions, when you add them, are also even functions. So if you wanted a more exotic example, y equals x squared plus 5 cos of x would be an even function. So it's a nice class of functions that all share this symmetry across x equals 0. Begs the question, of course, what does an odd function look like? Well, an odd function has almost the same rule as even functions, except there's a negative sign out front here. So what that's saying is if we plug in x equals some number into f, we can get the same height back but negative if we plug in the opposite x, or the negative version of that same x. And what does this look like? Well, it's symmetric through a point, which is a bit of a different kind of symmetry than we're used to. But it's a symmetry through the origin. We'll see what that looks like here. That didn't work at all. Let's try that again. There we go. There, and there. So one example, let's pick the easiest one, y equals x. That's a nice straight line, like so. And if we look at any point, let's say x equals 1, and then I plug in the point -1, I'm going to get -1 back. We could also do another example, like doesn't have to be y equals x exactly. It could be y equals 10x. So notice there can be even numbers in an odd function. It's more about the exponent that we're talking about here. So let's take a look at that, like so maybe. Oops. There we go. So those would be odd functions. Another odd function that is quite frequently seen would be y equals sine of x. Y equals sine of x goes up and then back down, and goes down then back up. And every point that we pick on the sine graph, let's say a point up here, if we go to the -x, it flips upside down. And that's where that symmetry through the origin comes in. If I go to the negative side with x, I also go to the negative side with y, and that is the same, or can be represented graphically as a reflection through the center, through the origin. Other examples would be y equals x cubed, or again a sum. Sums of odd functions are also odd. And scalings as well. Vertical scalings doesn't change the features. Horizontal scalings also don't change that property of being odd. Now, the interesting thing is when we get into integration, which is obviously our focus for this unit, a property of odd functions that we can see when we integrate on both sides of x equals 0 becomes apparent very quickly. Let's take our first example there, y equals x. There we go. Oops. It's supposed to make it straight by default, but sometimes it's a little dodgy. There we go. Let's try that one more time. There we go. So if we were to find the integral, say, to some later point a here, and we were to go the same distance on the other side, remember that this would have a negative component or negative contribution to the integral. And over here, we would have a positive contribution to the integral. And guess what? The areas are of identical size, which implies that the integral from minus a to a of here, it's just, this graph is y equals x, but it's true for any odd function. We're going to get an area of 0 for any odd function. And if you like, you could say, oh, it's worth saying. Let's do it. Because we can split our integral into the two components, minus a to 0, and the integral from 0 to positive a. And because these are equal in size or magnitude, but opposite in sign because the function is odd, that's what makes this sum equal 0 when we simplify it. So this again comes up surprisingly often, especially in a lot of physics modeling, sometimes in biology and business, but most typically in physics, where you have all these ideas of symmetry appearing quite frequently. Now, even functions maybe aren't quite as exciting. We like zeros because they simplify our lives. When we look at even functions, it's not quite as nice, but we do see a pattern. Let's take, for example, y equals x squared. Looks like that. Then if we integrate it for the same distance on both sides of x equals 0, then the best we can do there is notice that these are equal area zones on each side, and so the integral from minus a to a of, let's call this g of x if it's even, to distinguish it from the last one, will be the same as maybe an easier integral, just half the interval, but times 2 because of the symmetry. If, and again here's the big if g of x happens to be an even function, there we go. So that's a brief reintroduction for most of you to even and odd functions. You'll see some assignment questions that relate to this, and in particular you'll see assignment questions where we leverage the properties of even and oddness of a function to simplify an integration process.